Now, in the previous lecture we have defined what is approximation, we have also defined what is the best approximation. If we take a function like p x is equal to some c naught phi 0 x plus c 1 phi 1 x plus so on c n phi n x, then we define this as the best approximation if it minimizes the error norm. Therefore, this is the best approximation if p x minimizes the error norm, and the error norm we have written it as error f vector c of the constants norm of f x minus c naught phi 0 c 1 phi 1 plus so on c n phi n. Now, if we define the norm suitable norm, then we get different type of approximation. We mentioned that if we use the Euclidean norm, we get the least square approximation, and if you use the uniform norm, you get the uniform approximation. So, let us again just define what is our Euclidean norm for this function to derive the least square approximation. So, let us define the least squares approximation. Therefore, we need to define what is our approximation first. F x is equal to p x, approximately p x, that is your c naught phi 0 x plus c 1 phi 1 x plus so on c n phi n x. Let us denote the error as simply E. Now, I will write it as only E, that is inside this norm. So, that is your f x minus p x, that is f x, this quantity f x minus c naught phi naught plus c 1 phi 1 plus so on c n phi n. Now, since we want to use the Euclidean norm, what we shall do is that the square of these errors, then sum up. If there is a weight function, multiply by the weight function also. Therefore, the total aggregate of the errors over the interval a b is now minimized. Therefore, we define the least square approximation as that the total squares of the errors, that is the aggregate of the error W x into E square, where W x is a weight function, is greater than 0, is a weight function, is minimized. Therefore, the total squares of the errors, that means the total aggregate of the errors W x E square, where W x greater than 0 is a weight function, is minimized. In many applications we just take the weight function as 1, therefore, it will be simply minimizing the aggregate of the errors E square over the entire interval that is given to us. Now, why we are using this is how the Euclidean norm gives this. Let us just look at what is the definition of Euclidean norm. The Euclidean norm of a vector, say vector x that we have, then we have defined this as norm of x is equal to summation of I is 1 to n W x k or W x I magnitude of x I square whole to the power of half. This is the definition of the Euclidean norm of a vector x. I can square both sides and write it also. Norm of x whole square is simply summation I is 1 to n W x I magnitude of x I square. Now, in our application this vector x is nothing but the error vector. So, this x is replaced by the error vector, and therefore, we are minimizing this particular quantity. If we are minimizing this norm, we are minimizing the square of it, both are the same. Therefore, we shall be minimizing this. Therefore, our x in this application is our error vector E that we have here. Therefore, by the definition of this, that the least square approximation definition, we can immediately say that we minimize, therefore, we minimize this summation. Let us write k is equal to 0 to n w x k E x k square. Now, since our data is let us write it as x k f k, k is equal to 0 1 2 3 n. That is why summation is running from 0 to n here, since our data is running from k is equal to 0 to n, and we have taken the data as x k f k. Now, let us denote this by some I. Let us just write this as I. I is equal to a function of the constants C naught, C 1, C 2, C n, because E contains your error, and this is your k is equal to 0 to n w x k E x k square. Now, let us write down what is E x k. So, I can write this as summation of w x k. Now, we shall remember that is k is 0 to n. So, let us drop that notation, just write down summation here. This is error of x k, that is f at x k minus C naught phi 0 of x k plus so on C n phi n of x k, all of them evaluated at x k, and this square. This should be minimum. This should be minimum. Therefore, it is a simple minimization problem of calculus. So, we require that the partial derivative of I with respect to the constant C naught, C 1, C 2, C n should be equal to 0, in order that it has a minimum or a maximum. So, we shall show that it is a minimum that is required later on. So, therefore, for a minimum we need delta I by delta C I is equal to 0 for all I is equal to 0 1 2 so on n. Therefore, we will have n plus 1 equations for determining C naught, C 1, C 2, C n. Let us now differentiate this with respect to I. So, I can differentiate this with respect to I, delta I by delta C I, that will be equal to summation of, we have a 2 here. So, let us write w x k, this is f of x k minus C naught phi 0 of x k plus so on C n phi n of x k and multiplied this by this is, now I have differentiated with respect to C I. Therefore, I will get phi I x k as a multiplicative factor with a negative sign. Let us put it in a bracket, phi I of x k, and this should be equal to 0. Delta I by delta C I must be equal to 0. Now, let us simplify this equation. We cancel 2 this and then take this term to the right hand side. So, I will retain this on the left hand side. Therefore, this will give us C 0 summation phi 0 into phi I, this is phi 0 x k phi I x k, and of course, w x k is also there. So, the first term will be C 0 phi 0 phi I x k, both of them evaluated at x k multiplied by x k, then plus C 1 phi, that is next term is phi 1 of x k multiply by phi I of x k, then we multiply by w x k this plus so on. The last term will be C n phi n, this is phi n of x k, this is phi I of x k into w x k. This is the left hand side that we have written, and this term f x k goes to the right hand side. So, I can write this as summation of w x k f x k phi I x k. And I running from 0, 1, 3 n. Now, these are n plus 1 equations in n plus 1 unknowns. These are n plus 1 equations in n plus 1 unknowns, C naught, C 1, C 2, C n. So, these are n plus 1 equations in n plus 1 unknowns, and these are called the normal equations. We call them as normal equations. Therefore, in any particular problem, when once our phi I are given to us, weight function is given to us, we just evaluate these sums over here and then substitute it over, solve the n plus 1 equations in n plus 1 unknowns, and then substitute back in p x for the values of C naught, C 1, C n, and that gives us the least square approximation. And we can also find out the least square error. We can write down the expression, we can substitute the values of C naught, C 1, C 2, C n over here, just simplify the whole thing, square this one, multiply by x k and sum over this, and that gives you the least square error, the total least square error. Therefore, if I put this as 1, then I can say that the substitute the values of C naught, C 1, C n in 1 to find the least square error, that is the total error that we have committed under the least square approximation we would get by substituting the values of C naught, C 1, C 2, C n in this particular equation. Now, let us take some simple case. Let us take the particular case of when which we would like to normally use as a polynomial approximation. Now, let us take the case when phi I is simply equal to x I. That means, the functions that we are talking, phi 0 is 1, phi 1 is x, phi 2 is x squared, so on, phi n is equal to x to the power of n. Now, let us substitute this in the equations that we have just now obtained here, and we have here phi 0 is 1, then we have got here phi I x k into w x k, then you have C 1, this is phi 1 is equal to x. So, we are going to substitute phi 0 is 1, phi 1 is equal to x, phi I is equal to x to the power of I. So, if I just substitute it over here, what I would get here is, now let us see the first term that comes out over here, and also we can still particularize it. I will let us take w x also as 1, w x also as 1. Then we can see that the first coefficient will be w x is 1, this is your 1, and you are now multiplying by the first equation for I is equal to 0. For I is equal to 0, this is phi 0 square, then we have phi 0 square is 1 square. Therefore, what you have here is the first term will look like C naught summation of 1, C naught, this is phi 0 square into 1, this is your C naught of 1, that is a total summation is the total values I is equal to 0, 1 up to n. Therefore, this will be simply equal to C naught into n plus 1. This is the total observations that we have here. Therefore, the first term here would be C 0 into n plus 1. Then we are taking the case I is equal to 0, therefore, this is 1, this is x and this is C 1, therefore, this is summation of x k, therefore, plus C 1 summation of x k. Now, if I take the next term, this will be C 2, phi 2 is multiplying by phi 0 and phi 2 is multiplying by phi 0, that is x square, that is x k square. Therefore, the next term will be plus C 2 summation of x k squared plus C n summation x k to the power of n. And the right hand side is for I is equal to 0, this is 1, f x k, this is 1. So, simply summation of f x k. So, the right hand side is simply summation of f x k. This is your first equation. The second equation I will take I is equal to 1. When I take I is equal to 1 in this, then I am multiplying phi 0 by phi 1. Therefore, I am multiplying 1 by x, this is 1, and the next term will be phi 1 into phi 1, that is phi 1 square, that is your x square, and so on. Therefore, the next term will be C naught summation x k plus C 1 summation x k square plus on C n summation x k to the power of n plus 1. On the right hand side, we have got here phi I, that is phi 1, that is x. Therefore, I will be multiplying by x k on the right hand side. This is your x k f of x k. You can now see that each one of them, because it is a polynomial, these will be just be last term of this will be coming here, and then this will come here, and then next term will be, if you are taking the next equation, you will have here C naught phi naught into phi 2, that is your x square into 1. So, the next equation would therefore read as C 0 summation x k square plus C 1 summation x k cubed plus so on C n summation x k n plus 2, that is summation x k square f x k, and so on. The last equation reads C 0 summation x k to the power of n, C 1 summation x k to the power of n plus 1 plus so on C n summation x k to the power of 2 n, that is n plus n, that is 2 n, and this is x k to the power of n f of x k. These are the normal equations when you take it as a polynomial. What we have taken here is p x, we have taken it as a polynomial C naught plus C 1 x plus C 2 x squared plus so on C n x to the power of n. So, this is the polynomial approximation that we have taken here. Let us see how trivial it looks like in the particular cases. Let us take the linear case. From here, let us just write down the linear least square a polynomial approximation. That means, I am just taking my polynomial as simply C naught plus C 1 x. Therefore, in this system that I had written it, I will just cut out the terms up to only two coefficients C naught and C 1. Therefore, the normal equations in this case would become, the normal equations are or n plus 1 C naught plus C 1 summation of x k is summation of f x k, C naught summation of x k plus C 1 summation x k square is summation x k f x k. Now, in any given data we just have to find what is the summation of x k, summation of x k square, summation of f x k and summation of this x k f x k, solve the 2 by 2 equations and we have the solution for C naught and C 1, and that will give you the least square approximation. And if I want the least square error, I would substitute in the expression that we have written it in equation 1, and we can find out what is the total least square error under this linear approximation. Now, if I want a quadratic approximation, that is 2, I will have one more term over here, C 2 summation x k square, we will have C 2 summation x k cubed, and you will have one more equation. Okay, let us write down the quadratic also. So, let us write this as quadratic approximation. Therefore, this will give us n plus 1 C naught, C 1 summation x k plus C 2 summation x k square is summation f x k. So, that will be our first normal equation. Then I have C 0 summation x k, C 1 summation x k square plus C 2 summation x k cubed is summation x k f x k, and the third equation is C naught summation x k square plus C 1 summation x k cubed plus C 2 summation x k 4, that is equal to summation x k square f x k. These will be the normal equations in the case of the quadratic approximation. Now, we can normally go up to cubic or a fourth degree approximation or any approximation. However, the one disadvantage of the polynomial approximation, we are talking about the polynomial approximation, is that when you take this system of equations in the for a very large n, system of equations become ill conditioned. That means, the solution is prone to the effect of the round off errors, that even if you have a minor round off errors in any of these numbers, that the cumulative effect of that will be destroying the solution. So, the disadvantage of high degree polynomial approximation is that the system of equations is ill conditioned. Therefore, we do not normally use beyond a degree or 3 or 4 in the least square approximation. So, that is the disadvantage of the least square polynomial approximation of polynomial approximation. That the normal equations become ill conditioned for large n. What really computationally, as I said, it would mean is that the round off errors that is there in your f x k, x k, and then these summations that we are doing, the round off errors can really spoil the solution of the particular problem. That means, if you round off to 4 places, you may get a different answer, you round off to 5 decimal places, you will get a different answer. So, that is the effect of the round error is seriously felt in the solution of the problem. That is what we really mean by ill conditionedness in terms of the computational aspect. Now, let us first take an example on this. Now, find a least square let us take a straight line approximation, straight line fit for the data x f x 1 3 1.5, 4.75, 2, 7, 2.5, 9.75. Let us also say find the least squares error. Find the least square error. Now, here we have asked for a straight line fit. Therefore, what we are talking of is approximation by using the polynomial C naught plus C 1 x. Now, the problem is very simple. So, we just have to find these quantities, these 4 quantities, substitute it and solve it here. So, I need here the quantity summation of x k, that is the sum of all these x's. I would give this value, that is equal to 7.5. Then I square all these numbers and then take the summation. So, I will have here summation of x k square, that is we are squaring these abscissa and then summing up, and this comes out to be 13.75. Then I need summation of f k, that is sum of these numbers. So, I will have summation of f x k, and this comes out to be 25.25. And lastly, we need the sum of these products x k f k, that is this into this, 1 into 3 and so on, and then sum up, that is your x k f of x k, and this is 48.125. Summation f x k is the, we are writing the product of these two.
So summation x k is 6.5. Summation x k.
Summation x k is equal to 7.5. 6 point, okay. Yes, 6.5. Using these values of the summations, we shall write down the normal equations. The data points are 5 points. So, your 5 times C naught plus 6.5 C 1, and that is equal to summation of x k 25.25. This is 6.5 C naught plus summation x k square is 13.75 C 1, and that is equal to 48.125. Now, you can solve this for C naught and C 1, and then you substitute in the, we want to find out what is the least square error. The least square error definition was summation of, here w x is equal to 1, therefore, this is simply f of x k minus C naught plus C 1 x k whole square. This is f x minus p 1 x, so f x k minus C naught plus C 1 x k whole square. Now, we have got the values of C naught and C 1 over here. Now, we have got the data points x k f k, we can substitute in this entire and then find out the total error in the least square this one. Now, we would like to repeat that this is not fitting the data, this whatever we have got here, the approximation is not fitting this data at all. It is not an interpolating polynomial, it is only an approximation to this function that is representing this data. Therefore, there is least square error. If it was an interpolation, this is exactly fitting this. Therefore, this there is no error in fitting this particular data, but this is an approximation. Therefore, even if you just write down a, say, a quadratic polynomial, artificially take quadratic polynomial, write down the values and write down fit a straight line from there, we would still get the least square error here. Because what would really would mean is, if I take the graph of this and let us say we have taken points like this, point like this, point like this, then what we are fitting is some straight line like this for this, such that the total squares of these errors, you see these are the errors, this is the straight line that we have now approximated for the function. Now, the error is this particular part here with respect to this point, this is the error, this is the error, this is the error. Now, this least square error is sum of squares of all these errors is your this. So, we are not fitting this function exactly for this data, it is a approximation to the function which must be representing that particular data. So, that is why we have this least square errors in the problem, and this is the best approximation because we have minimized the sum of the squares of the errors. Therefore, we have got that best value of C naught C 1 which minimizes this least square error. If you take any other straight line, for example, here we would get error which is larger than this particular error because this is minimized. Let us now discuss how we can apply the least square approximation as we have defined earlier when a continuous function is given. Let us take continuous function as f x. Therefore, I will again write our I is of C naught C 1 C n. Now, if you just look at this, what we have done in the previous case, this is we have minimized this particular expression. This is nothing but the summation. If you change the summation to the integral for continuous functions, this will be simply in an integral form. So, we will convert this into an integral form and write this as, that is integral given interval a to b, that is your first point, a naught is your first point, a naught is your first point and b is your last point x n. So, an interval a b is given here. So, which corresponds to that one. This is equal to w x weight function and multiplied f x minus c naught phi naught c n phi n whole squared dx, where I have written phi I is equal to function of x. This is a phi is a function of x because it is a continuous function. Now, again the for a minimum the necessary condition is that the partial derivative of I with respect to C I must be equal to 0 for I is equal to 1 2 for 0 1 2 n. Now, let us differentiate this with respect to C I partially. So, I would get integral a to b 2 times w x f x minus c naught phi naught plus so on c n phi n c n phi n, and derivative of this is phi I dx. With a negative sign, let us put this minus sign, that is here outside. This is equal to 0, is equal to 0. Now, again we will retain the integrals with respect to C naught C 1 on the left hand side and we take this to the right hand side. Therefore, I can write this as C naught integral a to b cancel of 2 also. So, I would here have phi 0 phi I w x dx, that is the first term. This is phi 0 into phi I into w x plus C 1 integral a to b, next one is phi 1, this is phi I and this w x dx plus so on. The last term will be C n C n a to b, this last one is phi n. So, phi n into phi I w x. On the right hand side we have w x f x phi I. So, this integral goes to the right hand side, this is your w x f x phi I dx. Now, I would like to write down all these values for phi is equal to 0 1 2 because we would like to make some observations on that. Let us take the case I is equal to 0, then this gives us C 0 a to b phi 0 square I is equal to 0, therefore, we have phi 0 square w x dx C 1 integral a to b, this is I is 0, this is phi 0 phi 1. So, I will have phi 0 phi 1 w x dx plus so on, C n is outside, integral a to b, this is phi 0, this is phi n, phi 0 phi n w x dx. On the right hand side we have w x f x phi 0 dx. I would like to write one more equation. Therefore, this will be C 0 integral a to b. Now, this is I is equal to 1. Therefore, I will now get phi 0 phi 1 w x dx C 1 a to b. Now, this is 1. Therefore, this is phi 1 square. Therefore, I will have here phi 1 square w x dx plus so on C n integral a to b. Now, this is last term is now this is phi 1 into phi n, phi 1 into phi n w x dx, and the right hand side is a to b w x f x phi 1 dx. Now, let us write down the last equation I is equal to n. I will therefore have integral a to b phi 0 phi n w x dx plus C 1 a to b phi 1 phi n w x dx plus C n a to b phi n square w x dx is integral a to b w x f x phi n dx. Now, these give us the required n plus 1 equations in n plus 1 unknowns. I have to evaluate these integrals, all these integrals, they are all functions of x. I can integrate all of them, and once I integrate it, I substitute it over here and then find out what is my C 0 plus C 1 is. Therefore, this gives us n plus 1 equations in n plus 1 unknowns. Now, let us again take a particular case here. There will be two particular cases I would like to discuss here. Let us take the case 1 as simply phi I is equal to x I. Let us take again phi I is equal to x I is equal to 0 1 so on n. So, we are taking phi 0 again as 1, phi 1 is equal to x and so on, phi n is equal to x to the power of n. Now, let us get the approximation linear polynomial approximation. Therefore, we are considering the case p 1 x is equal to C 0 plus C 1 x. Therefore, our phi 0 is 1 and phi 1 is equal to x. Now, I just have to substitute these values over here, phi 0 is 1, phi 1 is equal to x, and then retain only two terms, there are only two unknowns C 0 and C 1, and then I can write down the equations. Therefore, the first equation will read as C 0 integral a to b w x into phi 0 square, that is simply 1, therefore, it is w x plus C 1 integral a to b w x. The second term is your phi 0 phi 1 w x dx. Therefore, I will have product as x, therefore, I will have here x into dx, and the right hand side is integral a to b. Again your phi 0 is 1 here. So, I simply have w x f x here. So, I will have here w x f x dx, and the second equation is C 0 integral a to b w x x dx plus C 1 a to b w x. Now, this is x square, phi 1 square dx, phi 1 square is x square, and the right hand side is integral a to b w x x f x dx. So, I just again have to evaluate these integrals, then solve for C 0 C 1, and then we have the required linear polynomial approximation. I can again find out the total least square error also using this one. Similarly, I can write down the quadratic polynomial from here by just taking one more term in this, but the reason why we made it into case 1 and case 2 is we mentioned earlier that these functions phi 0 phi 1 is our choice. If our choice makes the things better, then we would prefer that. In the previous case we have seen, we have taken the linear approximation or quadratic, then high degree, then we said the system of equations become ill conditioned for large n. However, if we choose these functions phi zeros as orthogonal polynomials, orthogonal with respect to the weight function w x, then there is no ill conditionedness that comes there, because the solution comes directly. Let us see what would happen in this case. Let us write down this, let phi x be orthogonal polynomials. Let us take them as orthogonal polynomials. Now, what is the definition of orthogonal polynomial? The definition of this is integral a to b, it has a weight function w x, phi I x, phi j x dx is equal to 0 for I not equal to j. These functions are orthogonal with respect to a weight function over the interval a to b, that is for I not equal to j the integral is 0. For I is equal to j, it has some value, that value depends on what that particular polynomial is, but we are interested mainly in this particular property. For example, if you are choosing the Legendre polynomials here, if we are taking the Legendre polynomials p n x, p 0 p 1 p 2, that Legendre polynomials p n x, then in that case the weight function for this is 1, weight function is 1, the interval a b is minus 1 to 1. That means, what we are saying is integral minus 1 to 1 p m x p n x dx is equal to 0 for m not equal to n. This is the property of the Legendre polynomials. I can choose other polynomials. The other polynomial that is very useful is the Chebyshev polynomial. It is called a Chebyshev polynomial. That is, it is denoted by T n x. In this case, the weight function for Chebyshev polynomial is 1 upon under root 1 minus x square. The interval a b is equal to minus 1 to 1. Now, we are going to define the Legendre and Chebyshev polynomials in the next lecture, because this we are going to use it later on in numerical integration also. We are going to use them, very important. These are very important polynomials. It has Chebyshev polynomials have very important property, that if you take the magnitude of this over the interval and approximate it by any of the function, the error on this will be minimum compared to any polynomial over that particular interval, but that we will discuss it slightly later. Now, what this really means is, if I take integral minus 1 to 1 T m x T n x by under root of 1 minus x square, that is your w x t m x t n x dx is equal to 0 for m not equal to n. Now, we shall show that if I choose these coordinate functions phi I as the orthogonal polynomials, then everything gets immediately simplified. Let us see why it is so. Let us just go back the previous equations which you have written the entire set. Now, let us put your orthogonal polynomial here. The orthogonal polynomial here, if I put it here, this is phi 0 square w x, this is phi I phi j, I is equal to j is equal to 0. Therefore, this is a non-zero quantity. Phi 0 phi 1 by definition it is 0, all of them are 0, the right hand side is there. Therefore, the first equation simply gives C 0 a to b phi 0 x w x dx is equal to this, and hence I found out C 0. Go to the next equation. By definition again phi 0 phi 1 w x is 0, integral is 0, this integral exists, this integral vanishes. Therefore, except if you look at this as your matrix, except your diagonal elements, this is C 0, C 1, C 2 diagonal elements, all the off diagonal elements are going to be 0 because of the orthogonal property. Therefore, I can immediately determine my C i's without any solving a system of equations. The trouble arose in the previous case, we are now solving a system of equations there which turned out to be ill conditioned system. Here there is no question of solving the system of equations. What I would therefore have here is, I will have here C 0 integral a to b phi 0 square w x dx is equal to the right hand side a to b w x f x phi 0 dx and so on. I will therefore have C I is equal, we can write down the denominator as integral a to b phi I square w x dx. So, I am taking this coefficient and putting it in the denominator, and in the numerator you have a to b w x f x phi I dx for I is equal to 0 1 so on n. Therefore, here it is just simply evaluating the integrals, and then the ratio of these integrals will immediately give you the value of C I, and hence there is no ill conditionedness does not arise here. Does not arise if we choose phi I as orthogonal polynomials. Now, we could of course as well have chosen in the previous case also, the discrete data case also, phi x is orthogonal polynomial. The answer is yes. In that case, instead of integral a to b of this one, you will have summation over k w x k phi I x k phi j x k dx is equal to 0. So, I could as well have used this orthogonal polynomials in the discrete data set also, where from we will use, as I said, I will replace this integral by summation, and therefore, we can find out C I there also by just taking the ratio of two summations also. So, the use of the orthogonal properties in the least square approximation is very useful, and in particular if you have a continuous function, it is the values of these integrals, these are available for us when m is equal to n, we can straight away use those property of the orthogonal polynomials to arrive at the approximations. So, we will take the example next time.